Hello, this is a review, a prep session review on kinetics that I did using a graphic organizer. And so I'm going to model this for you now. So we're going to start with our topic, kinetics. And kinetics, I don't know that you can see that. There we go. Kinetics is all about a rate. And rate is about the change in concentration over the change in time. And as we go through this graphic organizer, I'm going to use just a model equation, a model reaction here, like this. All right, let's back up a little bit, see if we can still keep that on. All right, so we're going to divide up problem solving in kinetics into three categories. And this first category is going to be just simple arithmetic. And another way that we're going to problem solve in kinetics will be puzzle or problem solving. And the third way we're going to problem solve with kinetics will be graphs. All right, so let's go back to our arithmetic category. We're going to talk about two different ways to problem solve in kinetics that just require some simple math, some simple arithmetic. And so first we're going to calculate the average rate, which is a measure of disappearance of reactants. That would be negative, or the appearance of the products, and that would be positive, per unit time. So I'm going to open the graphic organizer up, and we're going to talk about or give an example of how you might calculate an average rate. So if we had a data chart where we had time and the concentration of our reactant and the concentration of one of our products, and we measured the time and a reaction, and we went and we measured the molarities here, and we took a look at what happened between 50 seconds and 100 seconds. If we wanted to calculate the rate, the average rate, it would be equal to the disappearance of the reactant per unit time. So if we look from here to here, the difference would be 0.100, and the difference in time would be 50 seconds. And that would be disappearing, so it would have a negative sign. If we wanted to calculate the rate of the appearance of a product, then it would be the change in the concentration of one of the products over the change in time. And so looking back up here to our data chart, that would also be 0.1 over 50 seconds, and that would be positive because it's increasing. It's increasing. So simple arithmetic based off the data that's given. All right, a second way to problem solve with kinetics that just involves some simple arithmetic is relative rates. Relative rates, meaning as reactants disappear, the products appear. And this is dependent on stoichiometry of the reaction. So let's look at an example of a relative rate problem. So here's our average up here. Up here is our average rate calculation, and down here we're going to do a relative rate. Okay, so using the equation that we wrote here, using this equation that we wrote up here, we're going to relate how the reactants disappear to how the products appear. So as the concentration of the reactant changes over time, it's equal to the way that the concentration of the product changes over time, which is equal to the concentration of the other product changes over time. Now we have to be careful to account for the stoichiometry in the reaction, and we had 2 moles of this reactant, which produces 2 moles of this product to 1 mole of this product. So this is going to disappear at 1/2 the rate that this one would disappear, and this would appear at 1/2 the rate that this one would appear. These are appearing and this one is disappearing, hence the signs. So this tells you how the disappearance of the reactant relates to the appearance of the products. It gives you a relationship if you set this up, and then you can problem solve with it if you have data that has the change in the concentration of the change in time. All right, so let's go to the second type of problem solving that we'll have in kinetics, which is much like a puzzle. The first one we're going to look at is called the differential rate law. Okay, and the differential rate law has to do with the relationship which is written with rate and concentration data. So if you have rate and concentration data as opposed to time and concentration data, then the differential rate law is a good way to problem solve. So let's take a look at that. So we're going to look at the differential rate law. And it takes the form of rate is equal to the rate constant times the concentration of the reactants to some order. All right. A, in this case, the exponent is the order of the reaction, with a 0 order, meaning the change in concentration has no effect on the rate, and with an order of 1, meaning the change in concentration is proportional to the rate, meaning as the concentration goes up, the rate would go up proportionately, and an order of 2, meaning as the concentration doubles, then the rate would quadruple. So it would be to the square of, to get the overall orders, to get the overall order for a reaction, then you add the orders. If I had more than one reactant up here, then I would follow this with the concentration of the second reactant raised to a power which would signify the order of the reaction. All right, the next way we use puzzles to problem solve in kinetics would be a mechanism. A mechanism, which is simply a sequence. A mechanism is a sequence of bond making and bond breaking events. Okay, so we're going to look at an example of a mechanism. So a mechanism outlines the steps between what happens between the reactants and the products. So it talks about what's happening here at the yield sign. And remember, with a mechanism, it's the slow step that determines the rate law. Okay, it's the slow step that determines the rate law. So let's get two definitions down here, get them under our belts. Remember that an intermediate is produced and consumed. While a catalyst on the other hand, is not in the final reaction. It goes in and comes out. All right. So if we look at an example of the decomposition of hydrogen peroxide, so we have, of course, the reaction proceeds like this. If we were to just write a formula equation for it, and we would balance it like this. But we know that there's actually more happening at this yield sign than indicates for just the reaction. So the proposed sequence of steps here would be that the hydrogen peroxide molecule reacts with an iodide ion, which acts as a catalyst, by the way, to produce the iodine molecule and 2 molecules of water. And then the second step that happens at the yield side is that the iodine molecule reacts again with the hydrogen peroxide to get you 2 moles of the iodide ion plus oxygen. Because the iodine molecule is produced and consumed, it is an intermediate. All right. Because the iodide ion is not in the final reaction, it goes in and comes out, it is a catalyst. So if we get the overall reaction, what we have here is 2 moles of the peroxide molecule, which yields you 2 moles of water and 1 mole of oxygen. And that's a mechanism. So kind of a nice puzzle to solve. All right, the last type of kinetic problem solving would be graphs. So let's look at instantaneous rate. And that's where the rate is equal to the slope of a straight line tangent to a time versus concentration curve. So let's go inside and we'll draw one, kind of familiarize ourselves with it. So if we look at instantaneous rate, we've got this curve, graph, with concentration on the y-axis and time on the x. And we have a reactant, which is going to decrease over time like this. So we're going to put xy here. And we have a product, which is going to increase in time like this. And if we wanted to get an instantaneous rate, say, of the appearance of a product, we could take any line, any point on that line, and draw a tangent to that line and figure the rise over the run at that point, and that would give us the instantaneous rate of the appearance of a product. So we would take the change in y over change in x, which was the same thing as the rise over the run, which is the same thing as the slope, which is the same thing in this case as the rate, which is the change in concentration, y, over the change in time, x. the rate at that point, which is the instantaneous rate. So another type of graphing problem solving is the integrated rate law, which is a relationship written with concentration and time data, as opposed to our concentration and rate. For the differential rate law, we have concentration and time data. Okay, so for the integrated rate law, we're going to take that data, and if we graph the concentration versus the time and we get a line like this, the equation for that line is y is equal to mx plus b, because it is a straight line. And this tells us that this is a zero order rate, that the rate constant is equal to the negative slope. All right, so we needed to know the rate constant. If we can find the slope of this line, that'll give us the rate constant. And the concentration is equal to the rate constant times the temperature plus the initial concentration. Noticing that the y, the m, or the slope, the temperature, and the concentration. Two, natural log of the concentration over the time. This would, if we got a line, if we graphed the data and changed it to the concentration to the natural log of the concentration, we got a line that looks something like this. This would be at first order. So that, once again, the slope, the rate constant, is equal to the negative slope of that line, and the integrated rate law would be natural log, corresponding once again to the equation for a straight line. And if we graphed that data reciprocal of the concentration against the time, and we get a straight line like this, that's going to be a second order rate law, where the rate constant is equal to the slope. And the equation would look like this. Okay, once again, this corresponding to x being the time, and slope being the rate constant, and the y being either the concentration, the natural log of the concentration, or the reciprocal of the concentration, and the y-intercept being the initial concentration. All right, so we're going to turn this over. We're going to talk about some three other things that we need to touch base on when we're reviewing kinetics. Let's talk about the Arrhenius equation and the activation energy. If you take the natural log of the concentration and you graph that 1 over the temperature, you get a line like this. You can take the natural log of the rate constant, which is equal to the activation energy over the gas constant times the reciprocal of the temp plus the natural log of the concentration. This would be y is equal to mx plus b, where the slope, right, the slope would be equal to the activation energy over the gas constant, or if you wanted to solve for activation energy, is equal to the negative r times the slope, this being a constant. Another thing that needs to be reviewed in terms of kinetics is the half-life. Remember that most half-life reactions are first order. And the half-life can be determined if you know the rate constant by dividing the rate constant into 0.693. And you can derive this number, but since most half-life reactions are first order, and this is the equation for a first order reaction, it's kind of handy to know this. Finally, we need to talk about a catalyst and the function of a catalyst and how it works. So we have an energy curve that looks like this. Okay. We have a exothermic reaction where the energy of the reactants is higher than the energy of the products, and this reaction gives off energy. So from here to here is the change in enthalpy, or the delta H. And from here to here is the activation energy. It's the energy required to get that reaction started, going to reach the tip of the energy curve. The role of a catalyst is to provide an alternate pathway so that the activation energy can be lowered, like this. So a catalyst, while it goes in and comes out and doesn't affect the reaction, it does provide an opportunity for the activation energy to be lowered and for that reaction to occur faster. All right, I hope this will be a helpful instrument for your review for the AP exam. It kind of categorizes kinetics and talks about all the different ways that you can problem solve with kinetics, plus gives you a little bit of review on some of the things that are connected to kinetics. Thank you very much.